All right, cool, awesome. Yeah, so my talk is going to be on encryption as a service with Vault Transit Secrets Engine. So it kind of tails off of the last talk with talking about Vault and how to set it up in a POC. So I think it's a great transition, and the talk before was pretty awesome as well. Yeah, so go ahead and get started and just talk about the Vault Transit Secrets Engine. So the first thing I want to talk about is stop storing data in plain text. And this kind of talks, and this is why I want to talk about Vault and Transit in particular, because this can be crucial to your organization and your organization's data into your customers or users. Data leaks happen all the time, and a lot of time it is because data was stored in plain text. Some big companies have admitted to storing user data in plain text, including passwords, which make a hacker's job a lot easier when they don't have to try and decrypt the data that they've already gained access to. With the internet being a massive part of people's lives, it should be a default standard to make sure any data your company stores is encrypted at some measure, especially when you're dealing with the data of users. So the Vault Transit Secrets Engine makes it super straightforward as it brings such simplicity, such as limited key exposure, meaning that the encryption keys that you use in Vault never actually leave it. Instead, all data is sent to Vault through its API, which is another security measure, which should be done over TLS. And that'll get data encrypted, decrypted, signed, or verified. Another big benefit is that Transit provides a wide variety of reliable and consistent algorithms, which we'll dive into deeper. And then in the demo, I'll show a couple examples of them. So in the session, basically, I just want to dive into what the secrets, what the Transit engine can do, talk about some of its features, go through an example workflow, walk through setting up the engine because it's pretty straightforward, and then go through a live demo showcasing some of its features. Yeah, so like Jackie mentioned, my name is Jacob Mameliti. I'm a consultant at Arctic out of Toronto, Canada. I focus on enabling customers with HashiCorp tooling, specifically with Vault, Terraform, and Consul. And then I also spend a lot of time in the microservices space, working with all things Kubernetes, mostly on GKE and Anthos as a whole for Google. And I've also started developing a pretty keen interest in security and spending time working with customers on how they can improve their security practices in general, and especially with Vault. So a lot of talks recently have been around Transit and how they can encrypt data before they're sending it off to some sort of persistent storage. So you can find me on Twitter or GitHub with the handle there, so Arctic Jacob, and also by email, which is my first name dot last name at arctic.ca. And then I'll be posting these slides also on my GitHub as well as the code that I'll use into the demo. That's all on my GitHub public repo right now. So let's talk about the Transit Secrets Engine and just give a general overview. Basically, it's responsible for handling cryptographic functions on data in Transit. So think of Transit as encryption as a service or encryption as a service or cryptography as a service. Vault does not actually store any of the data sent to it. It just simply encrypts the data. Once the data is encrypted, it can be stored on some persistent data store. This is one of the most common use cases I see with Transit, as it relieves the burden of proper encryption decryption from developers of an application, and then pushes that onto the operators of Vault. Developers can now just be responsible for writing quality code. Anything sent to Transit to be encrypted must be base 64 encoded. So with that, anything that can be in fact base 64 decoded can be encrypted. The engine is not just limited to text. The Transit Secret Engine can also sign and verify data, which can be useful when it is required to digitally prove that some data was actually created by a specific entity. If you've ever downloaded some software before, you'll see that the ability to also download some hash, which can be used to verify the authenticity of the application, and that it hasn't been modified or corrupted in any way before it got to you, deeming it to be unsafe to run on your computer. It's usually a generally good practice to follow, as running unsigned code on a computer can potentially result in running something malicious. So in the upcoming demo, I'll go through an example of how to create a signature in Vault and go through a scenario where we get back a valid and invalid entry by changing the data that we send to Vault. Another benefit to Vault Transit Secret Engine is the ability to generate hashes of data. So we talked about that a bit earlier too. And it can also act as a source of random bytes, similar to for tools like 1Password, for example, that can generate random strings for passwords. This is also super useful feature if you just need a way to generate a truly random set of characters for something like a password. So one of the features of Vault that I find pretty useful, and I've seen some customers start to use it, adopt it more frequently, is the idea of convergent encryption. So this is a mode where a user can pass a set of plain text and what Vault deems as a context, and it'll get back the same ciphertext. Vault does this by deriving a key using a key derivation function. And because the key space that it uses is so large, the combination of plain text plus a ciphertext, the risk of generating the same ciphertext is pretty much near zero. A key use case for this is to allow encrypted data to be stored in a database so that rows with the same values for a specific field can be returned from a query. This is useful when a database has limited lookup or query support. Another way to think of this, and this is usually the example I give to most people, is if my application requires users to say reset their password ever so often, maybe like every couple months, and I don't want them to reuse a password that they've used in the past, I can keep a list of all their passwords used, encrypted, of course, like at the database level. And then when it's time for the user to change their password, I encrypt their potential new password and compare it to the previous passwords using a comparison of ciphertext. Here, convergent encryption allows me to never have to convert anything from ciphertext to plain text during that process. And then in the demo, again, I'll go through as well where I can pass the same data with a context, and the amount of times I hit the API, I'm always getting back that same ciphertext compared to when we're not using a convergent encryption key, we're getting back a different ciphertext every time. So like I mentioned, Transistor is becoming a bit more popular with some of the customers I'm working with because they were trying to integrate it into their application. So this is a diagram I like to show a lot. It kind of hits home and kind of paints a picture of what Transit can actually do. This is just a diagram found on HashiCorp's website. So I just want to talk to it. So let's pretend the way I do this is just kind of paint a scenario. So let's pretend we work at a company that has a Python web application. I'm just choosing Python specifically because that's what I'm using in the demo that is backed behind some SQL database. Right now, you have a team of 3 developers that are responsible for working on your application and making sure it stays updated. Right now, 2 of the developers are using their own methods for encrypting data by each using different Python libraries, and the 3rd developer isn't even using encryption at all. The problem with the situation is that there isn't any consistency, and when it comes to something like an audit of security measures, the spotlight is on the developers, which don't really have a good story based on what we just described. The other issue with this is that developers are also focused on having to think about the type of encryption to use. And again, this is being done at the development level when it really should be done at like some sort of security level. With Vault and Transit, developers no longer have to be responsible for this. Instead, they can be given 2 API endpoints to hit, one for encrypting data and one for decrypting it. The decisions of what types of encryption to use, how often the encryption keys are rotated and et cetera, can now be done at the Vault level and by a security team. This now allows the developers to solely focus on developing their application and do not have to spend time passing some security measure. Again, this is now passed on to the operators of Vault or some sort of security team, and all security compliances can be met at the Vault level, and this can now be easily audited without having to dive into some sort of source code and seeing what libraries developers are using. So looking more at this diagram and kind of walking through it, here's a workflow to encrypt data that this Python web application receives. And again, we're going to assume everything is over TLS encryption, and this will just help keep data encrypted in transit from the application to Vault initially when it's written in plain text. So on the far left over here, we have the application that sends its app data to Vault through its API. And request to have it encrypted. So this can be done through like the CLI, the actual web API, or Python has a HVAC library that I'll demo that's already built into Python's library. You just have to install it with pip. Second step will be Vault will encrypt that data and then send it back to the application. So we see the encrypted app data there. And then the third piece is the application will take this encrypted data, also known as ciphertext, and store it in some persistent data store, which in our case is some SQL database. Now on the reverse side, when a user requests to see their data that has been encrypted, the workflow would look something like this. The user requests that data and the application does a lookup by some primary key and returns the ciphertext from the database. So an example of this, if we need to look up a user's email or credit card or some sort of information, we can look it up by using like some sort of ID or like a username. The application must then connect to Vault and send the ciphertext to Vault through its API and request to have it decrypted. And then the third step is Vault will decrypt that data to plain text and send it back to the application, which can then print that data out to the user. So as you can see, Vault becomes an integral piece of the application and the database workflow. And one piece I left out here was how the application actually authenticates the Vault, which can be done with something like AppRoll, which is a much different conversation. And that's something I can answer questions about after, or if anyone's really interested in that, is reaching out. So let's get into actually enabling and using the secrets engine. So like enabling all the other secrets engines, enabling Transit is really straightforward. Everything in Vault is path-based, similar to how like Linux or Windows machines are set up. I've added a terminal on the right to show that the 3 steps, which enables the engine, creates an encryption key, and then encrypts it in example plain text snippet. On the first line, we're enabling the Transit engine and have created a path at the root level called Transit. Like I mentioned, everything in Vault is path-based and permissions are given out based on those paths through Vault policy. On the second line here, we create a key called demo key, which will create a new encryption key that can be used immediately and will encrypt any plain text sent to it using AES 256 GCM96 encryption. Transit supports multiple other keys such as AES, JCM, GCM with 128-bit or 256 like we're using, Cha-Cha 20 with a 256-bit key, RSA with 2048-bit or 4096-bit, and it also supports a few others, and the full list can be found on the Vault website. The final line encrypts an example plain text snippet with the created key above. In a more real-world situation and in the demo, this API endpoint is what we use to encrypt the data sent to it. It's up to the user to store that value and persist it somewhere, since Vault does not, like I mentioned earlier. Back in the previous slide, when I was mentioning that the developers would essentially need 2 endpoints, this would be the endpoint needed to encrypt that data. As you can see, the developer would not know that their data is being encrypted with AES 256, and they really don't need to. That's kind of one of the big parts of it. It's up to the Vault team to manage what encryption keys they use and when those keys get rotated. So the UI, so just kind of showing that Transit can also be used in the UI and how that kind of looks. Users have to also have the appropriate policy, which can create, view, edit, and delete encryption keys. There's plenty of other features available through the API that are also now available through the UI as well. Some users may find the web UI more efficient to look up the list of keys that are being used, the encryption key that they're using, and how often it's being rotated. It can be super crucial to see how often a key has been rotated to prevent data being encrypted with the same key for too long, as this can pose as some potential security risk. In the slide here, I show a page. I have a page shown that highlights all versions of the current selected key, which can provide a quick way to see how often it's actually being rotated. So you can see, for example, version 1 was created on February 15th at around 12:42, and then the second version was around 12:56. Due to Vault's strong ACL policies, Vault administrators can scope exactly what specific users can and can't do with Transit, and more specifically with encryption keys. The likely scenario is that a developer will not have access to see this page at all, and again, they shouldn't really need to. Developers' policies can be finely scoped so that they only have the ability to encrypt data and decrypt it with an encryption key that administrators have allowed them to. This goes back to the whole point I was mentioning earlier on developers no longer have to worry about keeping high encryption standards. That's now shifted to Vault and the security team. Cool, so that's pretty much it in terms of slides. And again, we can get those slides sent out as well if anyone wants to review them. But let's go into an actual demo and kind of what I was talking about earlier of how Vault actually works with Transit. So I have a Vault server already set up. I'm not going to go through the creation of anything like that. It's already set up, it's unsealed, basically ready to go. So I'm just going to go from the part where we want to enable Transit and basically build it off there. On the left, I have my Python application that we'll use as part of the demo. So the first thing we want to do is enable the secrets engine. So we're going to do vault secrets enable transit, and we get a success basically saying it's enabled. And then, like I showed in the slide, it's pretty straightforward just to set up some example keys. So we'll create our first one. So a transit key, and then this one will be an AES key. I'm just putting the type of encryption that we're using in the key name. Probably not ideal in a real world situation, but it's kind of just to show that we're using different types. And so we can identify which encryption method we're using with the key. So I'll go ahead and do that. And oops, just made a mistake here. It's keys. Okay, so we created our encryption key, and then we'll do the same thing. And this time we'll create a key that is using RSA. So go RSA 248. And then this time we're going to specify a type. By default, I didn't specify a type above, because by default it does AES 256. So go RSA 248. And okay, so there we go. Now we have two keys created, and then we can do a vault list transit keys, and we can see that our two keys have been created. So we'll go ahead and create and just do some basic encryption to show that it is in fact working and kind of how the workflow would go. So I'll go with my AES 256 key, and then I'll pass in some plain text. Again, everything has to be base 64 encoded. So I'm just wrapping it around that. And then we'll do like a sample in a credit card. So 1, 2, 3, 4, 1, 2, 3, 4. And we see we get back from Vault a key value pair with ciphertext and then the value, which is encrypted. And then what we can do is we can actually decrypt it, right? So we'll do a Vault transit decrypt. So again, we're hitting a different endpoint, and this is specifically the decryption endpoint, 256 key. So we specify which key we want to use, and then we're going to type in this time ciphertext, and then we can just grab this snippet here, paste that, and then we get back our value in base 64. So we can just echo this out and then base 64 decode it. So we'll pipe it to base 64 and then pass a decode. And then we see we get back our credit card. So this is great, except really not useful in a real world situation. What's more useful is how can we add transit into our already built applications. So like I mentioned, Vault already has a library for it in Python called the HVAC. So what we have to do is you have to do like a pip install HVAC into your environment is probably the easiest way I've seen. And then just import the library right here, like I've done on line 1. We do initial setup. So we're doing initial HVAC, which just defines some map that allows us to say, hey, this is where our API exists, where our Vault API exists. We're passing in a basic way to connect to Vault. And then more specifically, we have our two functions here. The first function is a transit encrypt, and then the second function is a transit decrypt. And basically all these functions are doing is they're taking in two variables each. One is taking in plain text, and then it's taking in an encryption key. So the idea is when I'm using my application, so for example, like a web form maybe, or how we're going to do it is basically I'm passing in my plain text as maybe a password. And I say I want to encrypt it with a specific key. Again, this could be abstracted. So you could basically just say that all developers would have to use key name A, and then they would just go ahead and use that. But it's pretty straightforward right here in that basically we take the plain text, we create a new variable called encoded text, which is basically just base 64 encoding it. And then we create another variable called ciphertext, which is actually using the HVAC library, and specifically it's reaching out to Vault. And you can see it's going into the secrets engines, it's going to transit exactly. And then it's encrypting the data by giving it the name. So it was the key to encrypt it with, and then the plain text. So it's very similar to how we set it up over here, where we have our key name, and then we have the plain text, which is already base 64 encoded, and then we get back our ciphertext. And then we can use that ciphertext to go ahead and save that in a database. So for this demo, I'm using like an SQL database to store it in. And then it goes for the other side. The other side is like a transit decrypt. So basically we are just reaching out to Vault with our ciphertext and our decryption key. And we're saying we need to get this back in plain text because we need to prompt it out to the user or something. So we can go ahead and do that. Again, it's pretty straightforward. It's just 4 lines here. Again, we're hitting the secrets engine, transit specifically, Sending our decrypt data. Again, we're passing in our name, which is the decrypt key we want to use, and then the ciphertext, which we're getting back from the database first. We're going to go ahead and decrypt it, base 64, decode it, and then send it out, and then use that information to send it out to the user. I won't go through go through all this because I'm also using like the Postgres dynamic credentials, which is kind of outside of scope for this, but it was just because I wanted to post this code for everyone to use. So it's a way to show best practice around that. But more specifically, like I said, I'm using Postgres to store this encrypted data. So when we go through the demo now of actually using this application, we'll log into the Postgres box and verify that that the data is being stored encrypted. So let's go ahead and test out this application. So we'll go ahead and do Python 3 app.py, and then we'll encrypt a password for myself, and then we'll use the AES 256 key. So we get prompted for a password. Again, this will be shown out in plain text, but that's okay. So it says successfully created new account for myself. So now if we head over to our another terminal and log into Postgres, so we'll go ahead and log in. We can now do a select all from users. And we can now see that our user is in fact stored in plain text with username Jacob M, and then that is our encrypted password. Right, so now we can see for developers, it's pretty straightforward, and that it wasn't up to them to create any additional libraries of seeing how this data is encrypted. They merely just had to use an encryption key that was likely given to them by some Vault team and saying, use this to encrypt our data. So on the other side of it is we can actually then decrypt this. So say, for example, we need to print out a user's email back to them. An easy way to go ahead and do this would just be Python 3 app.py, and then just how I have this set up, I'm using a decrypt flag, passing in my name and then the type of key that we are using. And now we see that the password for Jacob M is 12345. So again, what that's done is it's reached out to Vault. First, it's gone out to SQL, gone to ciphertext, and then reaching out to Vault and saying, can you decrypt this data with the key that I'm giving you? It's gone ahead and done that, and then it can print out our encrypted data back to us. So this was just an example of using a username and password. Likely you probably whereas something you'd want to probably print out to a user, like I said, is like some sort of email or phone number that they have, just some sort of sensitive data that you want to store, but may potentially need to actually output to the user. The final piece I just want to walk through pretty quickly is the idea of rotating a key. So rotating keys are pretty important in terms of saying we don't want to encrypt data with the same key over and over again. So it's pretty straightforward. We could just go ahead and do a vault write transit keys, and then we'll pass AES 256 key, and then rotate, and then passing the rotate endpoint. So now we've said success data written to that endpoint, and we've successfully rotated our key. So now if we do a vault read transit keys AES 256 key, we'll get some information about this, and specifically right here is our latest version. So now we see that a second version has been in fact created. And what we can do is, if we really want to update all of our ciphertext, we can rewrap anything that was encrypted with the version 1 and re-encrypt it with version 2. So we can go ahead and do that with a vault write transit rewrap AES 256 key, and then we're going to do with our ciphertext, and then we're going to go ahead and grab this right here. So this information we were using earlier. Go ahead and do that. And now we see that we've gotten back a new key value of ciphertext, and now more specifically, you can see V2. So we can see that we're using a second version of our encryption key. So we can see that it has in fact been rotated. And let's just verify that we can actually decrypt this still. So I'll do a transit decrypt AES 256 key, and then we can go ahead and pass in our cipher text, and we'll go ahead and copy this. Okay, and then again, we're getting back a base 64 encoded, so we can just go echo it out and then pipe it to base 64 -- decode, and then we get one, and then we get back like our sample credit card information. So One other thing I just want to show specifically was convergent encryption, like I mentioned earlier. So the ability to actually generate the same ciphertext based on a context and a plain text. So we'll go ahead and create a convergent key. So it's just transit keys convergent key. Just have to set this up. And then the one thing we do have to pass is convergent underscore encryption is equal to true. And then derived is equal to 2. And hopefully I didn't make any spelling mistakes. Okay, cool. And then we'll just go ahead and validate that this data actually is getting encrypted to the same ciphertext. So go ahead, write transit encrypt convergent key. And then we'll do our plain text is equal to, just go ahead and go with that, base 64. And then we'll go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, because it doesn't matter. And then we have to pass, like I mentioned, our context. So our context, again, has to be some sort of base 64 encoded. So base 64. And then we'll say our context is just random string. So again, if I typed everything correctly, we get back our ciphertext. And I can go ahead up arrow and place this again, and we can see that we're always getting back the same ciphertext as compared to if I just was encrypting data with a regular key that doesn't have conversion enabled, we would always get back a different value. Yeah, so that's pretty much it for the demo. It was kind of just wanting to show how transit can be used in general and more specifically with application teams.